I want to introduce the Metalog panel. So you saw, if I go back a second, this particular histogram, or I'm sorry, this particular Metalog distribution is an 8-term Metalog. And that is shown here where n equals 8 on this Metalog panel. Now what I'm showing here is all of the Metalogs from 2 to 16 terms, all plotted, each plotted individually. So you can see, if you go from a 2-term Metalog, that's a logistic distribution exactly, up to a 6, you can see there's a relatively stable set of representations there. N equals 6, 7, 8, 9. By the time you get to 11, now you've got a trimodal distribution, interestingly enough. 12, 13, 14, 15, 16, they're all trimodal. All right. Now, and then for n equals 10 and 16, the reason those are blank is those Metalog distributions are infeasible. And you'll see this pattern a lot. It will frequently happen that for a given set of data, you'll see blanks in your Metalog panel where the combination of the Metalog equation and that data using ordinary least squares is not feasible. Now, there are ways to make it feasible, like regularization, and I'll talk about that more in a minute. But for now, this is just a raw least squares fit to the data. Now, one aspect of interest here is to try to judge whether or not the, let's say 11, 12, 11 through 15 terms, is that a matter of overfitting or not, right? It could be argued, and particularly this gentleman, this researcher in finance, if he goes back and looks, he may actually find out that there is a third peak there, and the third peak is right around 0. So, in other words, gold is either likely to move a lot or a little, or not to move at all. Those would be the 3 basic scenarios. And the ones in between are less likely. That may be the story that he might end up coming up with. But largely, this is a matter of judgment based on the context. Now, and so the question is, are you overfitting? I've already pointed out the infeasibility. Regularization is another tool. What happens with any sort of least squares fitting is that as you start overfitting, there's a phenomenon called the Runge phenomenon, where the higher numbered A parameters in this case tend to get bigger and unreasonably bigger and alternating bigger. And one way to take care of that is to add a small positive multiple of the identity matrix. And that lambda is an extremely small positive number. It could be like 10 to the minus 5th or 10 to the minus 9th or something. And if you modify the Y transpose Y matrix before you invert it, then what you'll see is that you'll end up with dampening out the impact of those larger terms. So you can see now that 11, but by the time you get to 16 terms, you still have trimodality, but much less so and in a less pronounced way than those ones on the left. So regularization, I'm going to give you a tool for using regularization, and we can talk about this. The reference on this is Christopher Bishop, a book, he's with Microsoft, Pattern Recognition and Machine Learning. It's a great book if you're interested in learning about the statistical view of least squares fitting and many of the nuances for pattern recognition, which are critical, obviously, in machine learning. And he argues that there's a big overlap. It's not just statistics versus pattern recognition, that you actually need both. And I would highly recommend this book for those of you that may not have seen it.